Okay, let's go ahead and get started. Congratulations for making it in on such a cold morning. I have copies of the second problem set here for anyone who didn't pick them up. I also sent out an email, hopefully that you all got. Did anyone not get an email from me on Thursday? A statement regarding the academic policy. Did you not get that? You got that. You did not get that?
I got it.
You got it. Okay. Please read it and, take it seriously. I meant everything that I said in that email. I have paper copies. I guess I won't. Do you want me to hand out paper copies too, just so that we're all on the same page? Why don't I hand out paper copies too? So we're all on the same page. Please read this. Take everything that is in it seriously. I meant everything I said. If you have any questions or concerns, please feel free to get in touch with me or one of the TAs. Good. But hopefully we don't have to guess. Oh, copy of the problem set. Anyone else need a copy of the problem set? Okay. Please get in touch with me if you have any questions, comments, concerns, so on and so forth. But I would rather spend my time on physics, so let's go ahead and get started. So today we will be continuing our study of tensors. So last class we spent some time investigating three types of tensors that you are already familiar with, namely scalars, vectors, and one-forms. And at the end of class, we introduced the most general type of tensor. So let me just remind you again of the definition of the most general type of tensor. So a tensor of rank k, L, where k and L are 0, 1, 2, 3, and so forth, is a collection of d to the k plus L functions, where d is the dimension of our manifold, the dimension of space-time, which transform under coordinate transformations in a particular way. So if we wrote these d to the k plus L functions in a set of x mu coordinates as follows, you would label them by k plus L indices, k upper indices and L lower indices. So, for example, the upper indices could be mu1 up to mu k, and the lower indices nu1 up to nu L in, say, x mu coordinates. Then that would be related to the form of the tensor in primed coordinates as follows. So, in primed coordinates, you would again give the tensor by d to the k plus L functions, labeled by k upper and L lower indices, which are related to the components of the tensor in the unprimed coordinates by the multiplication by k Jacobian matrices and L inverse Jacobian matrices. So this is dx nu 1 divided by dx nu 1 prime all the way up to nu L. Times the original tensor in the unprimed coordinates. So mu1 up to mu k and nu1 up to nu L. So it's worth staring at this definition for a few minutes and making a few comments. So let me first remind you that a scalar tensor, or a 0, 0 tensor, is an object with no indices. that transforms in the completely intuitive way under a coordinate transformation. Namely, a scalar is an association of a number with each point in space-time, with each point in the manifold, and that's independent of whatever coordinate system you're in. A scalar has no indices, so there's none of these funny Jacobian factors that appear when you do a coordinate transformation. Now, a vector, or a contravariant vector, is a rank 1, 0 tensor, which has one upper index, and it transforms with a Jacobian matrix under a coordinate transformation. So this is just the generalization of the notion of a vector from your standard vector calculus class, where, as you probably remember, the components of a vector transform by the multiplication by a rotation matrix, for example, when you do a rotation. And that rotation matrix is just a particular example of a Jacobian matrix for a linear coordinate transformation where the coordinates are rotated in some way. Likewise, a one form is an object with a single lower index, which transforms with an inverse Jacobian matrix. And a tensor here, as I have defined it, is just the straightforward generalization of that idea to an object with many upper and lower indices. And tensors are the basic objects that we are going to be manipulating for the rest of this course. All of the laws of physics from this point on will be written as tensor equations. And so I would like to spend the rest of class today discussing tensors in generality, the various operations that one can perform on tensors, and so on and so forth. I should probably make a comment also about this rather horrific-looking formula here. At first sight, it might look rather difficult to remember the form of this formula, where the indices go when the indices are primed, unprimed, and so forth. But you just need to remember that the basic principle that one follows here is to balance the indices, and to make sure that in any equation that you write down, you have the right number of upper indices on the left and the right-hand sides of the equation, and the right number of lower indices on the right and left-hand side of this equation. So just remember that the Jacobian matrix has one upper and one lower index, and likewise the inverse Jacobian matrix. So here we have an equation which on its left-hand side has k primed upper indices and k primed lower indices. So when you write down the right-hand side of this equation, relating the primed tensor to the unprimed tensor, you'll quickly see that this combination of Jacobians and inverse Jacobians is the unique thing that you could write down, which has the right number of Jacobians and the right number of indices all contracted with one another. Are there any questions on that? Yes.
Actually, if you have a one-on-one tensor, d mu nu,
yes,
and you have mu and then a space, then mu on the bottom.
Yes.
What's the difference if you have
let me
space
let me comment on that. We'll spend the rest of class today discussing all such various issues of that form. Yes, good question. Let me come to that in just a minute. Before, I just want to remind you that k here is the number of upper indices, also sometimes referred to as the number of contravariant indices. And L is the number of covariant indices, which is to say the number of lower indices. Now, I don't tend to use the words contravariant and covariant because I always get them confused. I just use upper and lower. But I happen to have my notes here in front of me reminding me which ones are contravariant and covariant, so I'm telling it to you now, but do not expect to hear those words much for the rest of this course. Now, I should emphasize, as was already asked, that the order and placement of indices matters. And in particular, it could matter a great deal. So, for example, we could define a 1, 1 tensor with one upper and one lower index. And we could define a different 1, 1 tensor with an upper and a lower indices. upper and a lower index in opposite order. And those two things do not necessarily have to be equal to one another. Indeed, we will encounter many tensors throughout the course which are not symmetric under the interchange of the placement of the two indices. In fact, we have already encountered such tensors. You have known about such tensors for quite a while, although you have not known that you have known about such tensors. So in general, the order and the placement of the indices will matter. Likewise, if T with upper indices mu1 and mu2 will not be the same as T with upper indices mu2 and mu1. There could be special tensors where that happens to be the case. We have already encountered a special sort of tensor where that is the case, although we did not mention it explicitly at the time. And in general, if mu1 is equal to mu2, remember mu1 and mu2 are just indices that take values between 1 and d, or 0 and 3. So if mu1 is equal to mu2, then of course these two left-hand and right-hand side of this equation will always be equal. But in generally, it doesn't have to be the case. Now, when we discussed vectors and one-forms, we mentioned that it would sometimes be useful to use an index-free notation. So for vectors and tensors, for vectors and one-forms, we use the index-free notation, where a vector could be written as a differential operator, v mu d by d x mu, and a one-form could be written as an infinitesimal displacement, w mu dx mu. So analogously, sometimes people use an index-free notation for a general tensor. So you could write a general tensor as, so if you have a rank k comma L tensor with k upper indices and L lower indices, if you wanted to, you could think of that as some horrifying sort of object, which can be written in index-free notation as a combination of k derivatives and L infinitesimal displacements. And now, of course, you need some way of multiplying together these derivatives and infinitesimal displacements. There's a formal sort of multiplication that you can use to do so, which is called the tensor product. So this x with a circle around it is referred to as the tensor product. And so occasionally in your lives you may see people talking about tensors in this index-free notation. Generally speaking, I won't use this index-free notation. I don't think it adds too much to the discussion. But, for example, if you have, we will occasionally see it. The times that you might most commonly see it are when you're dealing with a tensor with two lower and no upper indices. So, for example, that tensor might be called G, and you might see an expression like G is G mu nu dx mu tensor dx nu. So this, of course, will remind you of our expression for the metric of space-time. ds squared is G mu nu dx mu dx nu. So people will sometimes use this abstract index-free notation for tensors. You know, I suppose if you're an extremely abstract-minded person, then the index-free notation is elegant and enjoyable, but generally speaking, I don't think it's terribly illuminating. And so I won't use index-free notation in this course. There is a set of words associated with this index-free notation. So just as we say that vectors live in the tangent space and one forms live in the dual tangent space, you can say that a rank k comma L tensor lives in the kth power of the tangent space times the lth power of the cotangent space. As far as we're concerned, those are just a bunch of abstract words that won't have too much meaning for us. Any questions? I don't want you to stare too hard at this expression here and try and understand what it means. It doesn't really mean anything. It just means, the set of all tensors, right? I mean, it doesn't mean anything that you don't already know. Any questions? Okay. Now, I told you that we're going to formulate all of the laws of physics in this course in terms of tensors. So, because of that, it's very important to understand what sort of operations I can perform on tensors. What can you do to tensors in order to form another tensor? Because those are the sorts of operations that I'll have to use to build up our laws of physics. Now, many of these operations may be obvious to you. Some of them may not be. But I'll go through them all in a little bit of detail just to make sure that we're all on the same page. So what could we do to tensors? Well, we can add together two tensors of the same rank in order to get another tensor of that rank. So, for example, if T1 is a tensor with mu1 with k upper indices and L upper indices, and so is T2, then so is the sum of those two guys. Why is that true? Well, remember the definition of a tensor is something that transforms by multiplication by a bunch of Jacobians and inverse Jacobians. And if you think about it for a second, the multiplication by these Jacobians is a linear operation. So if T1 and T2 both transform in a given way under coordinate transformations, so will their sum. So it makes sense to write down things like the sum of two tensors of the same rank. Now, it does not make sense to write down things like the sum of tensors of different rank. That's why when we write down equations, we need to be careful that every term in the equation has the same number of free indices. Because if it doesn't have the same number of free indices, it's not a tensor equation, and that equation doesn't have any coordinate independent meaning. So it's important to follow these rules and be careful about the placement of indices in order to make sure that when you're writing down equations, you're writing down equations that have a meaning independent of the coordinate system that you use to write them down. Okay, now we can also multiply tensors. And we can multiply tensors of different rank. So, for example, if T1 is a tensor of rank KL, and T2 is a tensor of rank, MN, then this guy, their product, is a tensor of rank K plus M, comma, L plus N. That's just because it's an object with K plus M upper indices and L plus N lower indices. We discussed this multiplication earlier when we imagined multiplying together a vector and a one form in the most general way possible. You've also seen this multiplication before. You can multiply a vector and a scalar to get a vector, a one form and a scalar to get a one form, and so on and so forth. You could multiply a one form and a one form together to get a 0, 2 tensor, for example. You're already familiar with this. dx mu times dx nu forms the basis of 0, 2 tensors. Finally, the third operation that we're already familiar with is that we can contract the indices. And in particular, we can contract an upper and a lower index of a rank k, L tensor to get a tensor of rank k minus 1, L minus 1. So, for example, if you have a tensor with k upper indices, you could choose one of those indices and contract it with one of the lower indices. And by contract, of course, I just mean sum over. Now, why does that give you a tensor? Well, it gives you a tensor for the reason that we worked out several times last class, namely that the Jacobian with an index contracted against the inverse Jacobian will cancel, because the inverse Jacobian is the inverse of the Jacobian as a matrix. And so the two of them multiply together to get the identity matrix. Now, of course, there are many, many different ways that you can contract indices together. You could contract the first upper index with the first lower index, the second upper index with the first lower index, and so on and so forth. And all of those different ways of contracting indices will give you different sorts of tensors. Now, at this point in the discussion, you can see why people sometimes use an index-free notation, because you get tired of writing down all of these indices all the time. Occasionally, I'll be lazy and just write a bunch of dots instead of indices. But hopefully, it'll always be clear what we'll be talking about. What else could... Yes, question.
I've seen the second operation of tensor multiplication. How do you know in which order to put the new indices on the index?
Well, that's an excellent question. So this, for example, would be a tensor where I have k indices, then L indices, then M indices, then N indices. So you just need to put them in exactly the same order as you did before. Good question. Good question. Now, for many of the tensors that we'll be dealing with, for some of the tensors that we'll be dealing with, the order and the placement of the indices will not matter, but for some of the other tensors that we'll be dealing with, the order and the placement does matter. So we'll meet very quickly some tensors where the order and the placement is very important. Good question. Any other questions? Yes.
Like in matrix multiplication, like we cannot just arbitrarily multiply in any way, right? They have
That's
to
correct.
Be like specific n times m times m times k something. So is there any restrictions on tensors?
Excellent. So you're discussing the case of matrices that are not square matrices?
No, I mean like the ones that are not like the rows of the
Yeah.
first one is not equal to the column. So
Right. So you're discussing that's it. Okay, let me. Essentially, what you're talking about is accounted for by rule number 3 that you only contract an upper and a lower index. So in matrix multiplication, as you say, there's certain allowed and disallowed ways of multiplying matrices. That is all accounted for by this rule. So in the language, in this index notation that we're using here, these matrices that you're referring to would have some upper and some lower indices. And the rule that we use to decide when we can multiply them together is precisely the rule that you're only allowed to sum an upper and a lower index. This is the nice thing about the Einstein summation notation. If you're careful, it does not let you write down incorrect formulas. Because you're only summing an upper and a lower index together, you guarantee the Jacobians cancel. You guarantee that you get expressions that are independent of the coordinate system that you write them in. Any other questions? Good question. Okay, what other operations could we imagine doing on tensors? So far I've told you about operations that you're already familiar with. There are some other operations that you can imagine, but probably are not quite so familiar with. So we can also symmetrize and anti-symmetrize the indices. So what do I mean when I say symmetrize and anti-symmetrize indices? Well, so let's just first introduce a definition. So a permutation, sigma, what is a permutation? A permutation of sigma is a reordering of some set of numbers. So say the numbers 1 up to d. So a permutation of d elements, a permutation of d numbers is, I can't spell numbers correctly, is a reordering of the numbers 1 to d to, say, sigma 1 up to sigma of d. And it's a special fact about permutations that every permutation is a product of interchanges, where you just interchange pairs of elements. Are you guys familiar with this fact? Have you seen this fact before? Raise your hand if you've seen this fact before. If you haven't seen this fact before, play around with it. Write down write down your favorite permutation of the numbers 1 up to 4, and then write that as a product of interchanges of individual elements, pairs of elements. So then, what does it mean to symmetrize a set of indices? So we can then imagine symmetrizing a set of indices as follows. So the symbol that we use when we symmetrize some collection of indices is the following. So if T is a tensor, say with a bunch of lower indices mu1 up to mu L, then we will write the symmetrization of those indices using a set of round brackets, a set of parentheses. And that is the sum over all permutations sigma of T sub sigma of mu1 up to sigma of mu L. Now, there are L factorial possible permutations of these L indices. So it's conventional to multiply by a factor of 1 over L factorial out front to account for that. Just so that the operation of symmetrization remains linear. Likewise, we can anti-symmetrize, which is usually denoted using square brackets. And that is the sum over all permutations of T of sigma mu1 up to sigma of mu L. But here we introduce a sign. So we multiply times the sign of the permutation. And what is the definition of the sign of a permutation? So the sign of a permutation is equal to plus 1 if sigma is a product of an even number of flips. So an even number of interchanges. And minus 1 if sigma is a product of an odd number of interchanges. So it's a fact which you can easily check yourself that any permutation is given by a product of a number of flips, a number of interchanges of two elements, and it's always given by either an odd or an even number. So no matter how you write a given permutation as a number of interchanges, it will always be a product of either an even number of interchanges or an odd number of interchanges. So this is the definition of the symmetrization and the anti-symmetrization of a tensor. And of course, although I've written here the symmetrization and the anti-symmetrization of a collection of lower indices, we can do this so we can symmetrize or anti-symmetrize upper or lower indices and if we want to, we can also anti-symmetrize or symmetrize only a subset of the indices. For example, if you wanted to write down the symmetrization of something with, say, two upper and one lower index, you could write the following. It would be 1/2 t mu1 mu2 nu plus t mu2 mu1 nu. Or if you wanted to write down the corresponding anti-symmetrization, there would just be a minus sign here, because the second permutation there is a flip, single flip, which has odd sign. And if you want to, you can even symmetrize or anti-symmetrize indices that are not next to each other. So, for example, you could imagine if you have some tensor with 3 upper and, say, 5 lower indices, you could symmetrize these two guys, anti-symmetrize those two guys, and if you really wanted to, you could symmetrize the first and the third upper index. So when we do that, we usually denote it like this. So this symbol means that we symmetrize mu1 and mu3 and leave mu2 alone. So occasionally, I'll use that notation, or you'll see people using that notation when you want to symmetrize indices that aren't next to each other. It's a bit of a cumbersome notation, so usually we'll go out of our way to try and only symmetrize or anti-symmetrize indices that are next to each other. Any questions? Many of the tensors, in fact, almost all of the tensors that we will meet in our study of general relativity will have some interesting symmetrization or anti-symmetrization properties. Yes?
Can you give an example? The red notation, if I want to symmetrize mu1, mu3, and mu3?
Usually we don't, you could, but usually we don't symmetrize tensors. We only symmetrize a collection of upper or a collection of lower indices. You could, of course, talk about symmetrizing upper and lower indices. We don't have a special notation for that, but you could talk about it if you wanted to. Yes, good question. So often you'll see me talk about a symmetric tensor or a anti-symmetric tensor. So what do I mean when I say that? So a symmetric or anti-symmetric tensor is one which is equal to its anti-symmetrization or symmetrization on all its indices. So we usually only talk about a symmetric or an anti-symmetric tensor if it has all upper or all lower indices. And in your lives as physicists, you have already met both symmetric and anti-symmetric tensors of various rank, although you haven't identified them as such. So what is the characteristic property of a symmetric or an anti-symmetric tensor? So a symmetric tensor is unchanged when you, that's supposed to be the word under, it's unchanged under the interchange of indices. So it's the generalization of the notion of a symmetric matrix, and an anti-symmetric tensor picks up a sign, and in particular it picks up a plus or a minus sign depending on the sign of the permutation under the interchange of indices, under a permutation of indices. In particular, it picks up a minus sign if you flip two of the indices. So that is the generalization of the notion of an antisymmetric matrix. In particular, it's easy enough to see that an antisymmetric matrix, an antisymmetric tensor, the component of an antisymmetric tensor with two equal indices is 0. Why is that? Well, it's equal to, so an antisymmetric tensor picks up a minus sign every time you interchange two indices. So an antisymmetric tensor with two equal indices is equal to minus itself, so it has to be equal to 0. You're familiar with this because if you have an antisymmetric matrix, its diagonal elements are all 0. So this is just the generalization of that fact. Now, I told you that you've already met several of these sorts of tensors in your life, so let me make that completely explicit. So, for example, the metric of spacetime is an object with two lower indices, and in particular, it is an object with two lower indices that is symmetric under the interchange of those indices. So it is a symmetric 0, 2 tensor. Why is it symmetric? Well, remember the metric is defined in terms of the line element, dx mu, dx nu. And this expression for the line element is symmetric when we interchange dx mu and dx nu. What other tensors have we met in our life? Well, I introduced the Kronecker delta symbol, which was equal to 1 if mu is equal to nu and 0 otherwise. So this is a 1, 1 tensor. Now here, I have been careful to write delta mu then with a space in front of the nu. But of course, I could have also written, of course, the Kronecker delta symbol is the same so for the Kronecker delta symbol, there's no ambiguity, and so I could write mu just above nu if I wanted to. Usually we try and be careful and remember the fact that tensors, the ordering and the placement of the indices matter. For the Kronecker delta symbol, there's really not much ambiguity. So we just will often be a little lazy and write the mu above the nu. What's another example of a tensor? So the electromagnetic field strength. You've probably encountered this in your class on EM waves. So that is a antisymmetric uh, 0, 2 tensor, which is usually denoted F mu nu. So F 0I is the packaging of the electric field, and Fij is the magnetic field, and you package it all together into a tensor, which is antisymmetric under the interchange of indices. We'll return to the electromagnetic field strength in a little bit. Now, it's worth pausing here and just stepping back for a second. So why have I been so careful in my discussion of tensors? Well, the important point is that in order to write the laws of physics, in a coordinate invariant way, which is to say, in a way such that the physics does not depend on the coordinate system one uses to write those equations, we must write them as tensor equations. Now, why is that? It's worth commenting on that for just a second. Because, as we saw, a tensor is not something that is unchanged under coordinate transformation, but rather it is something which changes in a specified way under coordinate transformation. So let's say that we have a law of physics which says that T mu 1 up to mu k, mu 1 up to mu L is equal to S mu 1 up to mu k, mu 1 up to mu L in one coordinate system. I don't know, so the right-hand side could be some version of Maxwell's equations, and the left-hand side could be some version of the charge and the current density. So what does this look like in another coordinate system? Well, if this is true in one coordinate system, and if this is a tensor equation, then that will imply that this is true in another coordinate system. So, in particular, if a tensor is equal to 0, if t minus s is equal to 0 in one coordinate system, then it's equal to 0 in every coordinate system. Because if you multiply 0 by a bunch of Jacobian matrices, you still get 0. So any laws that are written in tensor notation will be true in every coordinate system, and will take the same form in every coordinate system. So our guiding principle for the rest of this course is going to be that the laws of physics, and in particular the laws of general relativity, will be tensor equations. Now, we're going to spend the next few weeks investigating the consequences of this statement, and in particular we will see that this guiding principle will, along with a few other basic things we know about gravity, essentially uniquely fix the equations of motion of general relativity. We'll see that essentially, given this principle, there's only one possible thing, given a few other principles that we'll encounter along the way, that one could write down as an appropriate equation for general relativity. And indeed, this is probably one of the deepest and most important principles that we use when we write down laws of physics, not just in general relativity, but in physics generally. We have a symmetry principle, in this case the symmetry under coordinate transformations, and we write down the law of physics, the most general law we can, consistent with this principle and any other principles we wish to impose as well. Okay, now I've introduced the concept of tensor here. But, and I've shown you that there are certain operations, addition, multiplication, and so forth, that you're familiar with that go through relatively unchanged when we think about tensors. However, if you think about it, we still have a long way to go if we want to write down laws of physics in a coordinate invariant way using tensors. Because I've shown you about addition and multiplication, so we've done elementary school math in terms of tensors. We've even done a little bit of middle school math, algebra, and so forth using tensors. But what we really need is a calculus of tensor. What we really need to do is to be able to take derivatives and integrals of tensors. Why is that? Well, the equations of motion of physics are differential equations. They involve taking derivatives. So we need to know how to take derivatives of tensors in a way which is consistent with our principle of general covariance. And why is this tricky? This is tricky because the usual notion of derivative will not work. So, for example, let's imagine that we have a vector, v mu. That's got one upper index. So it is a 1, 0 tensor. So you could imagine constructing the following set of d-squared objects, which are the derivatives of the vector in a given coordinate system. So the vector will depend on where you are in space-time, so you could write it out in some coordinate system. It's a set of d functions, and you could take the matrix of derivatives of that set of d functions. That has one upper and one lower index according to the rules that we have written down. And you could ask whether that's a tensor. And the answer is no. I invite you to check that out yourself. It's easy enough to see. All you do is you write out this expression in a different coordinate system and try and relate it to the expression in the first coordinate system using your rules for how objects transform under coordinate transformation. You use the chain rule for the derivative and your expression for the Jacobian matrix acting on the vector, and you'll find that these two are related not by the linear multiplication by some Jacobian and inverse Jacobian matrices, but also by some term involving the second derivative of the coordinate transformation functions. So, our laws of physics need to be tensor equations, and they need to involve derivatives. All laws of physics involve derivatives, just about. So, but we don't know how to write them down yet, because we don't know how to take the derivative of a tensor to get another tensor. And so, this tensor calculus will be the subject of roughly the next week and a half of this class. I should note, however, that there are some cases where we do know how to take derivatives. So we do know how to take derivatives in some cases. So for example, if f is a scalar, which is to say a 0, 0 tensor, then d mu f, as we saw last class, is a 0, 1 tensor. So we already know that there are certain tensors where the usual notion of partial derivative does give a good way of taking derivatives. And so the first question that we would like to ask is whether there is a generalization of this notion which allows us to easily take derivatives of other sorts of tensors. And that is the subject that I will turn to now. And it is a subject that goes under the name of the theory of differential forms. So the theory of differential forms is a special type of tensor calculus. It is, in some sense, the easiest and most basic type of tensor calculus. Before I start delving into the subject of differential forms, let me pause and see if there are any questions. Any questions? We're really into the guts of it now. This is really, this week and next week are the times when we're really going to be getting into some gnarly mathematics. Just hold on to your hats, try and enjoy the ride. I appreciate that you may get bemused by a flurry of indices. Try and just, remain calm. Move your seats to an upright and locked position, lock your tray tables, so on and so forth. Any questions? Okay. I should make a comment on the theory of differential forms. So, in my mind, it is a shame and a crime that when you're taught multivariable calculus, you're not taught multivariable calculus in the language of differential forms. And that instead, you spend your time mucking around with vector calculus and so on and so forth. Because the theory of differential forms, if you're a physicist, is so incredibly widely applicable. Now, it would be possible for me to teach a class on general relativity without doing a brief detour into the theory of differential forms. However, I think the study of differential forms is so elegant and so important, and things look so much nicer when phrased in the language of differential forms, that there's no way that I could look myself in the mirror if I did not spend at least a little time telling you about the theory of differential forms. And that is what we're going to do today and next class. And I think there's a sense in which you really can't understand a lot of the differential geometry we'll encounter later in this class unless you think a little bit about the theory of differential forms. Okay, with all of that ado, what then is a differential form? So, a differential form is just a particular type of tensor. So, a completely antisymmetric (0, n) tensor is a rank n differential form. So is a differential form of rank n. Or sometimes we just call it an n form. So, for example, a scalar f is a 0 form. The object with one lower index that we encountered before is a 1 form. An object which is a tensor with 2 lower indices, that is antisymmetric under the interchange of those 2 indices, is a 2 form, and so on and so forth. So, for example, the electromagnetic field strength tensor that you met in your electromagnetism classes is a 2 form. So the theory of differential forms is especially useful in electromagnetism. So, how many degrees of freedom are contained in an n form? Namely, how many functions of the coordinates do we need to specify in order to uniquely specify a differential form of rank n? Well, let's imagine that we have a d-dimensional manifold. Then an n form is a collection of a bunch of functions which are labeled by a completely antisymmetric set of indices. And so how many such indices do we need to specify in order to uniquely specify that function? Well, for a 0 form, we need to specify one function. For a 1 form, we need to specify d functions if we're in d dimensions. For a 2 form, it's the number of degrees of freedom of an antisymmetric matrix, which is d times d minus 1, because there are d choices for the first index and d minus 1 for the second index, because the second index can't be equal to the first index, or else you would get 0. That's the discussion we had earlier. So in general, an n form will be a collection of d choose n, which is just a shorthand for d factorial over n factorial times d minus n factorial functions. Yes, there was a question. A differential form does not have to be an invertible matrix. So, for example, f mu nu is a 2 form with 2 indices. You could think of it as a matrix if you like. It doesn't have to be an invertible matrix. So no, it doesn't. For example, f mu nu could be 0. Okay, 0 as a d by d matrix is no. It doesn't. In general, it does not have to be invertible. Sometimes we'll want to demand that tensors are invertible. For example, when we talk about the metric, which is a symmetric 0, 2 tensor, we'll demand that it's invertible. Why will we demand that it's invertible? Well, otherwise stuff doesn't make sense. We'll get to that when we come to the theory of metrics. So there's an interesting special case here. So, for example, a D form is a differential form with the same number of indices as the dimension of your manifold. So that has D choose D independent components. D choose D, as you may see, using this formula, is just equal to 1. So just like a scalar, a D form has only 1 degree of freedom. That's an important fact that will come back to haunt us in the not-too-distant future. So why are differential forms interesting? Well, there are lots of special operations that one can perform on differential forms. The simple of which is a special sort of multiplication that you can perform on differential forms. So there is a special multiplication for differential forms, which is known as the wedge product. So how is the wedge product defined? So given a P form, say A mu 1 up to mu P, so which we could write, so although I don't usually use index-free notation is a lovely thing to do for differential forms. So given a P form A with components A mu 1 up to mu P, and say a Q form B with components B mu 1, let's call them nu 1 up to nu Q, then we can define a P plus Q form, which we'll call A wedge B, whose components are given as follows. So A wedge B is a P plus Q form, so it has P plus Q indices, which we'll call mu 1 up to mu p plus q. And what are they? Well, it's a kind of multiplication. So we'll have A times B. And A has p indices. So we'll take the first p indices. For A, B has q indices. So we'll take the next q indices and take them to be indices of B. And then, in order to get a differential form, it needs to be antisymmetric under all of its indices. So let's antisymmetrize it. Okay, that was easy enough. When you antisymmetrize, you get something which is antisymmetric, which by definition is a differential form. And there's a customary normalization factor that we put out front in order to make your lives difficult. So I'll multiply times p plus q factorial over p factorial q factorial. Question? Yes?
Since A and B are already antisymmetric, is it sufficient to get the right antisymmetry properties for the wedge product? Just antisymmetrize over one index of A and one index of B?
Yes. Yes, absolutely. So this expression that I've written is a tad redundant because A and B are already individually antisymmetric under their components. So of course you don't need to antisymmetrize over absolutely everything. You only need to do enough antisymmetrization to get an antisymmetric object. Yes. This normalization factor out front is just a matter of convention. When you get used to, when you start dealing with differential forms, you'll see just how useful this convention is. Okay, so just as we can use dx mu as a basis of one forms, so a basis of one forms is dx mu, we can take as our basis of two forms the tensors dx mu, wedge dx nu. So there are d times d minus 1 independent choices of this tensor because dx mu wedged with itself is equal to 0 because it is, dx mu wedge dx mu is both symmetric and antisymmetric under the interchange of indices. Likewise, a basis of three forms could be given by the d times d minus 1 times d minus 2 functions dx mu, wedge dx nu, wedge dx rho, and so on and so forth. So it's sometimes useful to think about tensors in an index-free notation, where, for example, we write omega as omega mu dx mu, and the electromagnetic field strength tensor, for example, could be written as F, which is F mu nu dx mu wedge dx nu, and so on and so forth. So we often will write differential forms in this basis-independent way. Now, in general, it's not terribly helpful to write a general tensor in a basis-independent way, but it is often very useful to write differential forms in a basis-independent way. We'll be writing down, for the rest of this class and part of next time, several expressions for differential forms written in a basis-independent way, and you'll see just how slick such expressions can be. Many of the horrendous expressions that you learned in your multivariable calculus classes can be written down almost instantaneously in a basis-independent way using the language of differential forms. Maxwell's equations, for example, can be written as a single equation using the language of differential forms. So there are probably a few comments to make regarding this wedge product. So the wedge product does not obey the law of commutativity. The wedge product is not commutative. So if you have the differential form dx0, for example, and you wedge it with dx1, then that is equal to minus dx1 wedge dx0. Because when you interchange any two indices, you pick up a minus sign because of the definition of the wedge product involving anti-symmetrization. Or more generally, if you have the one form df, remember, which is the one form with components d by dx mu of the scalar f, and you wedge it with another one form dg, then you get minus dg wedge df. And in general, with one forms, you pick up a minus sign every time you commute or you interchange two one forms. And one can use this to work out the general law that determines whether or not the wedge product of a P form and a Q form is commutative. And one can show, and indeed by one I mean you on your next problem set, that if A is a P form and B is a Q form, then the wedge product of A with B is related to the wedge product of B with A by a sign which is minus 1 to the P times Q. Any questions so far? So I realize in the last 10 minutes I've introduced what is essentially just a bunch of notation. And you may be wondering why I'm wasting my time introducing all of this notation. So why am I introducing the special notation for one forms, wedge products, and so forth? Yes, question.
If you have a D form and you wedge product that in one form, what do you get? You get 0.
Would it, a D in D dimensions? Yes. If you think about it, that should be clear. Why is, so a D form wedged with a 1 form is equal to 0. Why is it 0? Well, it's a D plus 1 form in D dimensions. So you have D plus 1 indices, each of which can take only one of D values, which means that two of the indices must be equal. And because it's anti-symmetric in all of its indices, it hence has to be 0. So yes, a D plus 1 form in D dimensions is 0. Good question. So why do we introduce the theory of differential forms? Well, the reason is that differential forms are easy to differentiate and integrate. Remember that in order to write down the laws of physics, we need to know how to take derivatives and integrals. And the whole point of differential forms is that it is very easy to take their derivatives and integrate them. So how do we do so? Well, in order to take a derivative of a differential form, to get another differential form, we introduce what is known as the exterior derivative. So the exterior derivative is an operation, which we usually denote by D, which takes a P form and takes its derivative of it in a way that gives you a P plus 1 form. So if I have a p-form A, then its derivative is denoted dA. So that's going to be a guy with p plus 1 indices. Well, and what is it? Well, I just take the partial derivative of A. So A has p indices. I take the derivative, I get another index, then I anti-symmetrize over all of the indices. And I introduce a factor in order to make your life difficult. And this is a p plus 1 form. Now, I told you not 20 minutes ago that in general, taking partial derivatives does not give you another tensor. However, when we're dealing with differential forms and we anti-symmetrize in this way, the partial derivative does give you a good derivative operation on tensors. And so it's easy to check that, for example, the derivative of a differential form will give you another differential form in this way. And that the point about this anti-symmetrization is that all of those uncomfortable additional terms in addition to the Jacobian would cancel out. So let's just see this. We only have a few minutes left. Let's just see this explicitly. So why is this true? Well, let's imagine the simplest case when A is a zero form. So if A is a scalar, so we usually call F a scalar F. Well, what is that guy? That's the guy whose components are d mu F. And that, as we have already seen, is a one form. So that's okay. So there was nothing really to check there. That's the check that we did last time when we checked that the derivative of a scalar transforms as a one form. So let's try the next case. So let's imagine that we have a one form omega. Let's take d of it. So that the mu nu component of it is d mu omega nu minus d nu omega mu. There's some factor of 2. I'm just going to forget about that factor of 2 for the time being. I'm the professor, you're the students. You need the factor of 2 when you do your problem sets. I can drop it whenever I want. That's I have a PhD. That's the right that you earn when you get a PhD. It's right. It says it right there on the degree. So that's the expression of the derivative of a one form. So let's see how this looks in a different coordinate system. So in a primed coordinate system, what does this look like? Well, this is d mu prime omega nu prime minus d mu prime omega mu prime. So let's write that out. So this is d mu prime of omega nu prime. So let's try and relate that to the unprimed coordinate system. So using the transformation rule for our one form omega, that is dx nu by dx nu prime, omega nu, and then we subtract off the same expression where nu prime and mu prime are interchanged. So then we can just use the rule, we can just use the product rule to expand this. So we have dx nu by dx nu prime, where the derivative acts on the first guy. Then we have the term where the derivative acts on, this derivative acts on that guy. And for this term, I will write out dx mu prime using the chain rule. So that's dx mu by dx mu prime d mu omega nu, and then minus the same thing with mu prime and nu prime interchanged. Okay.
Sorry,
Yeah.
where did you pick up that sign for the second term?
Plus, I'm sorry. Thank you. Okay. Well, let's look at this expression here. Well, this first term is symmetric under mu prime and nu prime by the equality of mixed partial derivatives. But then we're subtracting off the same thing with mu prime and nu prime interchanged. So that cancels when you subtract off the same thing with mu prime and nu prime interchanged. And what are we left with? Well, we're left with d mu omega nu times the usual two Jacobians that you always look for when you want the tensor transformation rule. And then we're subtracting off the interchange of mu and nu prime. So we see that indeed this is equal to the transformation rule for a two-form. The whole point being that the anti-symmetrization has subtracted off the factor here, which leads to the problem when you try and construct a tensor by taking the derivative of its components. Okay. So, in fact, the exterior derivative is something that you've encountered many times in your lives as physicists. And, in fact, when you studied vector calculus, you learned all sorts of ways of taking the derivatives of scalars and vectors, all of which were identical to the exterior derivative. This is something that I'll take a few minutes to explain next class. You have 48 hours, however, to figure it out. So if you can figure out how all of the various derivatives of vector calculus are in fact the same as the exterior derivative of differential forms, then you'll be one step ahead of the game. That's a nice exercise. So I'll stop here unless there are any questions. All right, see you Wednesday.